for an entire body. Now we're going to zero in and say, what about a single point or a very small area that's not necessarily representative of the entire body? So we're gonna take a few steps back and get a run up to this by examining whole bodies and defining a small area and looking how a force applied to a whole body might end up translating to the forces that we would need to apply to a small area, and then averaging that over or integrating that, adding that up over an entire cross-sectional area. So first of all, why do we care? We've already shown that average stresses are pretty easy to calculate. The reason we need to know state of stress at a given point is, first of all, a lot of times, especially if we're very close to the points of application of that stress, like the ends that are being gripped of a bar or something close to a stress concentrator, something we'll discuss in future chapters, we'll find that the stress at one point could be very, very different than another point on that same cross-sectional plane. And second of all, and maybe a follow-on of that, is fracture, something very important, and yield or deformation, especially permanent deformation, is a result of what's going on in that local area. So even if your average stress is, say, below the stress necessary to propagate a crack and fail the material, you could exceed that in a local area, start a crack growing, and then the stress concentration of the crack tip itself could cause it to propagate. So local stresses really are important when we're predicting failure and designing against it. So that's why we're looking at this. So let's start out with a whole body. So we've got this blob-shaped body, and it's subjected to a bunch of forces and moments. And we'll define a cross-section plane A, somewhere within the body, and somewhere on that plane we're going to define a little area delta A, which of course later on down the road we're going to shrink down even more. But for now it's some finite small area that is much smaller than the whole plane. So if we just look at that tiny area, we can imagine that some resultant force delta F is acting on that area delta A, and it's at some angle. And so we know that the inner body forces can be resolved into axial like N versus shear normal forces, normal and parallel forces. So we can take this delta F and we can resolve it into delta FT, tangential, and then delta FN, normal, and with some angle alpha between the two. And the total delta F force is the vector sum of the two. And it's going to have an orientation that is going to be related to the cosine of alpha by our typical rules of vectors and trig. So we can use our area, our small area delta A, and our small force delta F in its resolved tangential and normal components, and we can define an average over that small area using the same rules we did for averaged over an entire body cross-sectional area, an average normal stress, delta F normal over delta A, and an average shear, delta F tangential over delta A. Now in this case we only have one tangential force because we have a single delta F that is sort of that small component of the resolved forces acting on the body. So we've only got one tangential component in this case. We could it isn't like our previous example where we had two potential directions that would still contribute to shear. We have two directions, but there's only a force being applied in this case in one. Okay, if we wanted to get the stress at any discrete point, like a singular point that had no area, all we would have to do is take the limit of each of these two expressions as delta A approaches 0. And then we would get the state of normal and shear stress at that point. So there's the literal definition of shear via the tangential component and normal via the normal to the surface component at that area. So obviously we would have to know the stress at that particular point on the surface to define that. But that is the definition in terms of a discrete area. So we'll have something to work with. Now just to kind of give an example of how you might work with a smaller area that might be a subcomponent of a larger body, we can define 3 points A, B, and C as having these coordinate points on a coordinate axis system, where y is kind of in the vertical orientation of the page. So x is sticking out here, and you've got z. Sorry, x is here and z is coming out at us. Apologies. Let me get up. Z, x, right hand rule, x, y, z. Okay, we can, if we have a force defined by -10I plus 2k newtons, and we want to know what the mean normal and shear stresses acting on this plane are, we can follow those same rules of first defining a surface normal somehow, whatever our surface normal is. Dot that normal into our force to get the normal component, then subtract that from the force to get the tangential component. Then we would divide each of those force components by the area of this triangle and get our normal and shear stress components. So we can start with getting our surface normal. Easiest way to get a surface normal is to take the cross product of two vectors that are in the plane together. So we can take a vector from A to C, a vector from A to B. So subtract the 2 points and turn those into vectors leading from one to the other, cross them, and we can get, in this case, A cross AB cross AC gives us a vector D, which is by definition normal to this ABC plane. And it's definitely got some magnitude to it, so it isn't a unit vector normal. We can divide out its length to get a unit vector. So we have that down here. We can also observe, oddly enough, because the vector AB and AC literally define the sides of the triangle geometrically, we can equate the length of this vector to 2 times the triangular area. And so we can, that's a little bit of a shortcut if we wanted to get the vector D length and divide. But regardless, we now have our unit vector D hat, I guess we could call it. And then basically we just dot that into F, and F dot N directed in the N hat direction gives us a normal force component. I'm not going to talk through every one of these vector components, and of course then we define our tangential force as our normal force subtracted out of our original. So now we've got, all we've done is resolve a vector into 2 components, one normal to a given plane, one tangential. That's all we've done, and found the magnitudes. So to get our average over that small plane of our average normal force, so sigma mean is just going to be the magnitude of the normal component of the force divided by that area. So that's where finding the area of the triangle was somewhat useful. So we can actually use properties of vectors to get that triangular area if we needed to. And so basically doing now the normal component of the force divided by this smaller area, pretty similar to our average normal stress calculation method formula. And so we get 1.5 megapascals, and then we can do the same for tau mean, shear stress mean, as the tangential force component divided by the same area. So that was what we did with that small area in the bigger body. So far, we don't get a lot of difference in mean or average shear and normal stress versus stress at a point until we take that area and shrink it down. So that's really where we're going to see the difference at stress at a point versus average. And we can average over not just the whole area, but we can average over maybe a subcomponent. So we don't have to take that area all the way down to a singularity point. So like in this case, we could average over a small area. Look at trends. Let's take a little bit of a look at directions of forces, and I'll blow this up a little bit to make it a little easier to see. So if we cut a body in half and we look at the forces between the two bodies and we resolve them, say, into normal and tangential components, we know by Newton's third law that the forces versus an external coordinate system are going to be equal in magnitude but opposite in direction. So Fn for area A, and then Fn prime for area A prime on the other side of the cut, the other side, the other end of the body that we sectioned. They're pointed in opposite directions. If we look at their corresponding normal stresses, though, because their normal stresses are going to be those forces which come with their own directions, their opposite directions relative to, and I'll draw it here, an external coordinate system. All right, we'll call it our XYZ coordinate system. The surface normals, on the other hand, are going to be also pointing in opposite directions. So because we've got two different components of our stresses, depending on both the direction of the force. Up here we were looking for just magnitudes, that's why we have the absolute values, but generally speaking stresses do have direction just like forces. You're going to have the surface normals to these areas going in opposite directions, so the forces across these cut surface, these interior forces, have equal magnitude opposite directions, but their corresponding stresses have the same magnitude and the same sign, because we're dividing by, in the case of the opposite stress, the opposite force that's going in the other direction, it will also be divided by a surface normal that has that opposite sign. So we'll see that later when we start defining positive and negative stresses based on the face where we define the stress. In fact, that's coming up right here. Okay, so we're going to continue our standard definition of shear and normal stresses with respect to a small reference volume. And notice now we're going really small. We have a little cube and we've defined its edges as dx, dy, and dz. So these are already very small. We won't necessarily call them of differential size, but pretty small. So we've defined our x face as this one. So we've got A, B, C, D. This is our positive x face. Positive y face is up here, kind of oriented vertically. So x, y, and this face is z. Okay, so the surface normals to each of those are going to point in the x, y, and z direction. Now, that said, we can define a negative x face as the face that is going to have a surface normal pointed in the negative x direction. So, using our coding, our negative x face is going to be bounded by E, H, G, and F, and likewise for the others. So we can define positive stress directions as a force that would be pointed in a positive direction on a positive face or a negative direction on a negative face. And we're going to define a general subscript notation for all stresses. We've already talked about the subscript two-part subscript notation with respect to shear, as the first subscript being the face and the second being the direction, but we're going to do that for everything now, including normals. So everything is going to be defined as sigma sub this or that. So if I'm looking at my normal force in the positive direction on the positive x face, I would have sigma x for I'm on the positive x, I'm on the x face. In the x direction, I get sigma xx. So here's my normal stress in the x direction. If I'm looking at the shear stress resulting from a force in the y direction on the x face, I have this force on the x face, so this is sigma xy. If I've got a negative direction x force acting on the negative x face, I still have positive xx. Think of it as double negatives. And likewise, so that convention continues. So we have a little drawing. Shear stress, so here's a force acting in the positive y direction on the positive x face, it's positive. Here's a direction acting in the positive, a force acting in the positive x direction on the positive y face, it's also positive. Here's a force acting in the negative x direction on the negative y face, it's a positive shear. It's going to result in a positive shear stress. And we've already gone over positive normal stresses, which are otherwise known as tensile stresses. So you can tell they're pulling the material apart. They're going to cause a stretch. The negative shear stresses basically cause a sideways distortion. Positive shear stresses cause a sideways distortion just in the other direction. So they don't have any inherent difference in what they do to a material, squeezing versus stretching. They just cause distortion in one direction or the other. And of course, our negative axials or negative normal stresses result in compression. So here's a general, complete stress at a point notation. So you'll have a sigma, meaning stress, as opposed to strain. You'd have a little e, kind of script e if it was strain. The first subscript is the face. The second subscript is the axis to which the force is parallel, so which direction the force is pointing. You might have a point of application, so you'll have a parentheses with a point location. So in this case, you have the stress on the x face in the z direction at point 1, 2.2, negative 3.6. Direction by elasticity convention, so that's negative, so that means it's either it's on the x face pointing in the negative z direction, or it's on the x face pointing in the negative z direction, so that's negative. Magnitude is 32 megapascals. So that's everything you could want to know about that stress. Face, direction, other part of the direction, point of application, magnitude. All right, tensor notations. You noticed on our cube, we've got a lot of faces. We got 6 faces, and on each face we have 2 directions that we can assign shear, and then we can have positive or negative axial. So this gives us basically a 3-column, 3-row matrix, a tensor as opposed to a vector, to express our stress. So we can write it many different ways. So we can do all sigmas with x's and y's. So we can do, the rows being the faces and the columns being the directions. We can change to tau to remind ourselves that if our 2 subscripts are not the same, that we have shear. We don't need a different symbol to say that. We know that just simply not having the same direction of these indices means we're in shear instead of a normal stress, but we can write it that way. We can also use numbers instead of letters, and this becomes useful if we want to use those subscripts as counters to start populating matrices if we start doing some numerical computations. So we can default say that our x, y, and z directions are denoted by 1, 2, and 3, and so sigma 1, 1 becomes sigma xx, or the normal force in the x direction, and so on. So option 1, 2, and 3 are all equivalent ways to express stress. So another common state that we encounter is what's called plane stress. And so that means the stress is confined to a single plane. It has two conditions. One, we have no stresses that act normal to the plane. So if we have the xy plane, there's no sigma zz, there's no sigma, or there's no tau, no shear stress on the x face heading in the z direction. There's no shear stress on the y face heading in the z directions. Nothing's pointing in the z direction. Shear, regardless of which face it's originating on, it's not pointing, there's nothing pointing in the z direction. Furthermore, there are no shear stresses on the z face. Nothing's happening on the z face. Okay, it's free. It's completely unstressed. When do we encounter this in practice? Thin sections. So thin wall tubes, surfaces of materials, because the surface there's nothing to touch it to apply a stress unless there's a big pressure differential. Free surfaces are by definition in plane stress. So when you see something thin, you see a free surface, you can think, plane stress. So certain portions of that stress tensor are automatically zero in those cases. You can have plane stress in any plane, not just the orthogonal planes, but definitely you'll see references to plane stress, not just in the xy, but the yz and the xz. So plane stress conditions also make it a little bit easier to define certain relationships. So when we start looking at, say, at elasticity and relating stress and strain, we might start with a plane stress or plane strain condition to do our derivation, with the understanding that this would apply even if we added the other orthogonal directions to it. But in practice, there are those thin sections and surfaces that are by their very nature always in plane stress. And as you can probably guess, things in plane strain, where you can by definition have stress in every direction, those tend to happen in the middle of things. So when we get to the strain section, we'll take a look at things that tend to be in plane strain. So those real life aspects of the plane stress, plane strain applications are important as well, to just recognize when could we make that approximation, when would it likely be valid, because it does simplify our life quite a bit from a calculation standpoint. Okay, so let's take a volume element, that same little cube, dx, dy, dz. Let's apply, it looks like we don't have anything going on in the z direction here. I've got nothing on the z face, and I've got nothing pointing in it. So I've got this little volume element in plane stress, and I'm going to put it in static equilibrium. I'm not going to let it translate, rotate, okay? So I'm going to make the sum of the forces in the x, the sum of the forces in the y, and the sum of the moments about the origin all equal to 0. So I've defined stresses, but I know for static equilibrium I need forces. So I'm going to get forces, I'm going to use the definition, force stress equals force divided by area over which it's applied, and I'm going to use the dimensions of my little cube here. It may not be a cube because dx, dy, dz may not be exactly the same, but I'll define those face areas. So sum of the forces in the x, I'm going to take sigma xx and I'm going to multiply it by the area of the x face, which is dz times dy. I'm going to subtract tau yx, which is pointing in the, I'm going to add tau yx, which is also pointing in the positive x direction, and it's being applied on a face that is dx dx times dz, dx times dz. It's pointing in the positive x direction here, so positive x. And then I'm going to subtract tau yx. It's also acting on a face that's dx, dz, dx times dz in area. And likewise, sigma xx normal force times dz dy for an area. So that's everything that's pointing in the x direction. Stress times the area of the face that it's being applied to gives me a force. I sum the forces, I set them equal to 0. I do the same thing for the y direction. Now for moment, I'm going to do the same thing to get a force, and then I'm going to take the distance from each of those faces to the origin. So I'm going to have a little bit longer expression, and the only thing that's going to be different is I'm going to have effectively the radius vector from that resultant force from the stress down to the origin. So if I look at, for instance, the moment due to tau xy, so that's this guy. So here's tau xy. It's on the x face, it's acting in the y direction. So I would multiply it by dy times dz to get a force acting on the x face in the y direction, and then I'm going to multiply it by the radius vector from the origin to that face, which is dx over 2, because we have a dimension of dx, and so the origin's in the middle. So to get to the x face, I've gone dx over 2 distance in the positive x direction. So that's this term. If I did that for all of the other components that we could use to define moment, and remember, notice we're only taking the shear components, of course, because all of the normal forces have lines of action that converge right on the origin. So basically, I've only got the shear stresses and the sizes of their respective faces and the moment arm to get from the origin to that face. All of that has to be equal to 0 for static equilibrium. So if I combine terms for that moment expression, I would find that I would get this. Tau xy times dx dy dz equals tau yx dx dy dz. Well, this was all of the taus on the x face pointing in the y direction. It was only one of them. Well, two, sorry. Positive x face pointing in the positive y direction and negative x face pointing in the negative y direction. And then this is tau on the positive y face pointing in the positive y direction, and then the one on the negative y face pointing in the negative x direction. dx dy dz is equal to dx dy dz. It's the volume, and it's equal. So by definition, we just proved that by putting that volume element in static equilibrium, not letting it rotate, we've shown that tau xy has to be equal to tau yx. And by extrapolation, if we did this for any other plane stress condition or any other condition, actually, we would just say the sum of the moments about O in a given direction. We could show this for any general stress state when we put that little volume element in static equilibrium. So the shears, xy, yx, basically on either side of the matrix diagonal, are equal. That means the stress tensor is what we call symmetric. So we could say sigma ij equals sigma ji in our kind of matrix subscript notation. So if you're used to upper and lower triangles in a matrix, maybe from your Gaussian elimination, you know that the upper triangle is defined as those values, and the lower triangle here, they're equal to one another. They have to be the same. And of course, the diagonal represents our normal forces, which we can't necessarily say anything about. from this equilibrium. So that's important to know. The symmetry of the stress tensor simply comes out of the condition of equilibrium of our little volume element. Okay, so that's it for state of stress at a point. We're going to add one more concept to that in this lecture, and that is to include the effect of orientation. So we can have a plane, right? So like say we have this rod and we've embedded it in the ceiling. It's 30 millimeters in diameter, and we hung a 10 kilonewton weight from the end. Maybe we super glued it to the end there, eliminating any of those attachment point stressors there. And we can define some point here on some plane in the middle of that cylinder, and we can define the state of stress at that point. Maybe the stress is uniform over that. If it's well away from the attachment points, we can say it's equal to the average stress. Okay, great. And because the weight is parallel to the axis of the cylinder, we can say that it's all normal stress. There's no shear. But what if we look at a plane that's tilted a bit? What if we said, well, what if we defined this plane? It's tilted at an angle theta with respect to the axis of the cylinder. Well, now everything isn't axial anymore. The total stress is axial, but now we can say that with reference to that plane, there's a normal and a tangential component, and they're not non-zero. There's going to be one for each. So we can define a normal and a shear stress as a function, not just a position on any plane at a point for something that it doesn't have a uniform stress distribution, but we can define normal and shear as a function of the tilt of a plane with respect to the direction of applied stresses, or to a coordinate axis. And then we'll define the applied stresses with respect to that coordinate axis both. So let's see what happens when we apply this 10 kilonewtons to a plane that is perpendicular, to the direction of applied stress, and then one that's tilted at 20 degrees. So in our case, we're looking at that plane that's normal to the applied stress. We just have our area of pi over 4 times d squared. So we end up with nothing but normal stress. Shear is 0 in both the y-x and the y-z, both orthogonal directions. And we have 14.1 megapascals of normal stress. If we look at a plane that is at 20 degrees to that normal, so tilted up, say there was some defect in that cylinder. I don't know. Maybe it's a composite. Maybe it's made of 2 pieces of wood or something, right? And you made a bit of a bevel, and this is a glue plane where you've got two sections glued together, and you're worried now about the shear strength of that adhesive. A lot of adhesives fail in shear. So you want to know what the shear stress is on that plane, maybe. That's a very typical application where you would be concerned with resolved shear stress. So the stress is being applied normal, but you got a plane that could be a plane of weakness with a given orientation. So let's check out what the shear and normal stresses are on this 20-degree plane. Well, the first thing we do is we resolve the force vector. So we use 20 degrees and we use some geometry, we use some trig. So our normal stress is going to be at f cosine of 20, and our tangential will be at f sine of 20. So we have 9.4 kilonewtons and 3.42 kilonewtons. But the cross-sectional area has now changed because it's an ellipse instead of a circle. So we end up having to use our 20 degrees again and ratio to get our, that we basically elongated one of the 2 axes of the ellipse, our a squared plus b squared. One of them got longer. So rather than having r squared, we have our one original r times a somewhat longer second axis of the ellipse. So we have a little bit bigger cross-sectional area, so to get the shear and normal stresses on this tilted plane, we're going to divide our normal and tangential forces by this larger area, and we end up getting a normal force of 12.5 megapascals and a shear force of 4.55. So we've reduced the normal force some, but we've got a shear force that went from 0 to 4.55. So the proportional change, we increased the shear more than we decreased the normal, and that's simply because of the trig relationship. So we could compare this, for instance, to, say, the maximum shear stress that the cured adhesive is rated for. That would give us, that's one example. In certain materials, there are directions in which it is easiest to yield. And so understanding the direction of maximum shear gives us a way to relate to whether or not a material will yield. So that is actually a criteria of whether something is going to plastically rather than elastically deform. So we'll go further into understanding for stress states where we have applied shear and applied normal stresses. We'll look at ways that we can simplify this math to understand what the shear and normal stresses on any plane tilted at any angle with respect to the applied are for any kind of combination of shear and normal loading. Because different things can happen to a material depending on how much shear and normal stress it has on any given plane. And we'll use that to predict yield and failure for different materials. So that is it for state of stress at a point. And the next and last section of our stress chapter will be the differential equations of equilibrium. So for that next lecture, we'll start taking all of these little volume elements and shrinking them down, and then looking at developing expressions, differential expressions for our stress elements and relating them together, which will give us a basis to solve for later on if we have, say, a continuous expression for one or the other. We can integrate and solve those. So stay tuned for that.